Hi and welcome to this video where we're going to talk about condensation polymers and in particular polyamides and polyesters. This is a really important class of polymer and these polymers you will come across quite regularly in your exams. In fact, if there's not an exam question on a condensation polymer of some description, I would be highly surprised. Okay, so the principles to consider is first off that you need a difunctional molecule or molecules. So ones with functional groups on both ends. That's really important because if it only has one functional group, then once it's reacted, then it just makes a new molecule. But if it's got functional groups on both ends, then both ends can react and keep growing. So you can end up with a long chain forming. Now, these are polymers of esters and amides. And so we make them the same way we would make an ester or an amide. It just makes something bigger. So an ester would be made from a carboxylic acid or an acyl chloride and an alcohol. So if we have a dicarboxylic acid with a dialcohol or a diacyl chloride with a diol or a diacyl chloride with a diamine, then we can get these esters and amides forming. Now, it could involve one molecule, so you could have two different molecules, each with two functional groups on there, or you could have one molecule with two different functional groups on there. That's really common with amino acids. Okay, so what are we really looking for here? Well, let's consider a polyester for a moment. Okay, normally we would make an ester from an alcohol and a carboxylic acid, or an alcohol and an acyl chloride. You can do exactly the same thing if you have two functional groups on the molecule. So you could have a diol and a dicarboxylic acid, a diol and a diacyl chloride, or an alcohol and something else on the same molecule. Now, exactly how it looks will depend on what functional groups are present in the molecule. But let me show you an example. Okay, so this is a fairly straightforward polyester example. Okay, at the top on the left hand side I've got my dicarboxylic acid. It's got 6 carbons in total, and on the right hand side is my dialcohol, diol, in this case ethanediol. When we join them together, what we get is a condensation reaction. So just like any condensation reaction, we're going to take away the OH group from the carboxylic acid and the H from the alcohol and join them together. This is going to happen at both ends of the molecule. And so we end up with a long chain of two alternating chunks. So you've got the bit over here, which has come from the carboxylic acid, then the bit that's come from the alcohol, then the bit that's come from the carboxylic acid, then the bit that's come from the alcohol carboxylic acid, the alcohol carboxylic acid, etc., etc., etc. You also get a lot of water formed because every time those two molecules join, there's another molecule of water produced. So that can be quite important. It's not just one molecule of water. Okay, it's a lot of water. Now these are really common, and this is the sort of thing that you might expect to see. All right. There is another option as well, which involves having both functional groups on the same molecule. And I'll show you what that looks like too. So in this example, I've got a molecule which has both functional groups in the same molecule. Okay, so this has got a carboxylic acid and an alcohol in the one molecule. They join together in exactly the same way, but instead of having two different chains alternating, it's the same thing, just repeating over and over again. A couple of things I want you to see with this drawing though. First one is that all of the bits are linked through these ester links. Okay, so C double bond O and then O. So just like a normal ester, it's just that it continues on and on and on. Second thing I want you to see is that at the ends of the chains, I haven't put in an OH or anything like that. I've just drawn dashes. Now that's really important because this is a polymer, and those dashes show that the chain continues on beyond what you've drawn because you've only drawn a section of the polymer. And that is really, really important. It's so many people just put H's on the ends, and that's then not showing a section of a polymer. The other thing to be aware of is that in exam questions, often they will ask you to draw a certain number of repeating units. If they ask you to draw 3 repeating units, draw 3 repeating units. Don't draw 4 or 5 or 2. If they ask you to draw 2, just draw 2, okay? Because sometimes that can be the difference between excellence and merit. Okay, so the second type of condensation polymer is a polyamide. And polyamides are usually formed from diacyl chlorides and diamines. And so you get that polyamide. And again, you get the 2 alternating chains, just like the polyester. Now you can potentially have a molecule that has both functional groups on there and joins up. Most of the time we would call that an amino acid, and what they join up to form is a peptide. And please do have a look at my amino acids and peptides video for more details on that. But the diacyl chloride and diamine is the usual option for a polyamide polymer, not a naturally occurring peptide. So let's just have a quick look at that for a sec. Okay, so here we've got a 6-carbon diacyl chloride and a 6-carbon diamine. So you can see that there's an acyl chloride group on either end of the diacyl chloride. There's an amine group on either side of the diamine. So they join together through a condensation reaction. Remember, a condensation reaction is when smaller molecules join together to make a larger molecule with the production of a small byproduct such as water or HCl. In this case, it's HCl that's formed. And we have now our chain, which consists of alternating units. So we've got our amine and our, well, other way, acyl chloride unit. Okay, this particular molecule most of you would be more familiar with as nylon, and if we ever get back in the laboratory we will have a go at making this. This is really, really important industrially. The production of all of these sorts of polymers are really key, and they all follow the same thing. Now, when you look at this diagram, just a couple of things to note. Again, you can see that I've got dashes at either end of the chain to show that it's continuing on. It's not the end of the chain. The other thing to note, this is only 1 repeating unit that I've drawn. So if you're asked to draw 2 repeating units, you would need 2 lots of this. They're joined together in the middle. You can see that that is an amide link. So C double bond O and then NH. Okay, on to the final bit. Just like any ester or amide, condensation polymers, polyesters and polyamides, can be hydrolyzed. So remember, hydrolysis is the addition of water which breaks a molecule into pieces. And just like with the hydrolysis of an amide or an ester, we have to do this in either acidic or basic conditions. And the products are basically the same as what you would get with the hydrolysis of an ester or amide, with one slight difference. Well, no, actually no slight differences, other than to remember that you've got multiple functional groups on each molecule, so you need to consider what happens to each functional group. Okay, so if you think about esters, if we hydrolyze an ester, we get back a carboxylic acid and an alcohol. It's exactly the same thing with a polyester. In acidic conditions, you get exactly the alcohol and the carboxylic acid, or dialcohol and dicarboxylic acid, whatever it happens to be. In basic conditions, any carboxylic acid groups will become carboxylate anions. So if you've got a dicarboxylic acid, then you end up with a dicarboxylate anion. What does that look like? Just let me show you. Right, so here is a section of a polyester chain. And I wanted to show you this one because it's got this weird thing over here, which is a benzene ring. It's a hexagon with a circle inside it. And they do pop up quite often in polymer questions. You don't need to know anything about it, just draw it as written, and other than that, go with it. Okay, so if we're adding water, we're going to do this exactly the same as we would normally do with an ester, except you have to remember that there are multiple ester groups. So you're going to break it up in the middle of the ester chain, right there. And then you're going to add H and OH onto either end. Okay, so pretend we're adding a couple of waters. So we're going to add OH onto one, onto the next, and some H's. Okay, just like that. And that, if you basically break that up into two molecules, that's going to show you the original or the starting point for your chain. Okay, so we've got here we've got our dicarboxylic acid and our dialcohol formed. In acidic conditions, then that's exactly what you would get. In basic conditions, then the carboxylic acid groups are going to react, and you're going to get not one, but two carboxylate anions on that molecule. And that's it. Just that simple. With polyamides, it's very similar, except that you've got your ammonium groups, which can be protonated in acidic conditions. So that's it for me on condensation polymers. I hope you found this useful. For more on polyamides and the hydrolysis of those, please check out the video on amino acids because I spend a bit more time on it there. All right, best of luck. I'll see you next time.